Hi, this is the third lecture under Module 2, How Florida Soils Interact with Phosphorus, under the general series of Phosphorus in Agricultural Watersheds, Science and Application. Lecture 3 is the second in a series of 2 lectures on phosphorus dynamics as related to soil morphology and composition. Learning objectives for Lecture 3 are general familiarity with phosphate bonding mechanisms, understanding of how soil components interact with phosphorus, knowledge of relative phosphorus affinity for common soil components of Florida, and understanding how component distribution affects phosphorus dynamics. Lecture 3 will review the nature of phosphate bonding. It will cover some soil components and their P retention characteristics, including amorphous aluminum iron oxides, crystalline iron oxides, and secondary phyllosilicates. And we'll summarize at the end with a few take-home points and provide some references. In reviewing the nature of phosphate bonding, I'll start with surface complexation concepts. The outer sphere complex is one in which water molecules intervene between the sorbate, or what's in solution, and the sorbent, the mineral surface in our case. These are weak electrostatic bonds, and they include exchangeable ions, and this is what we would call the exchange complex for soils. This is a depiction of an outer sphere complex schematically, showing water molecules around, in this case, an exchangeable cation. Anions can also be in the exchange complex in the cases where there is a negative charge on the surface of the mineral involved. But because the attraction is mainly electrostatic, these cations can easily be replaced by other cations, and anions can easily be replaced by others on the exchange complex. In contrast, inner sphere complexes have no water molecules between the sorbate and the sorbent. Excuse me. They have strong ionic or covalent bonds established between the surface and the sorbate. And the adsorbed species actually becomes, you could consider, a part of the surface. And that process is sometimes termed specific adsorption. Here is a schematic depiction of a case where there's an inner sphere complex. This is between an iron oxide mineral and phosphate. And this shows that the phosphate is actually bonded with no intervening water, sharing, in this case, 2 oxygens with the constituents, the metal constituents in the mineral itself. This is a very strong attraction, and it would result in hysteresis or very slow desorption, a desorption that doesn't correspond to the adsorption loop. Phosphate mainly forms inner sphere complexes because it bonds strongly with metals, and that strong bonding results in stable surface complexes and in stable minerals. And this can be explained by the electron distribution and electronegativity. Here is a depiction of a phosphate anion, -3. The phosphorus is 4-fold coordinated, a tetrahedrally coordinated, 4 oxygens. There are 2 bonds with 1 oxygen due to the configuration of the outer shell electrons for phosphorus and oxygen. The negative charge is asymmetrical, that is, it's distributed more with the oxygen atoms to the exterior than it is to the phosphorus, which is on the interior. And that asymmetrical distribution in charge results in a high electronegativity for the anion, and that gives the phosphate anion a high level of reactivity. This is a schematic example of phosphate interstier complexes on iron or aluminum oxide mineral surfaces. The blue circles represent oxygen or hydroxyl. The M's represent aluminum or iron at the mineral surface. In the upper case, we have a single phosphate bonded through a single bond with a single metal in the mineral surface. The bond is through an oxygen or hydroxyl, and this is referred to as a monodentate association. In the middle case, we have a phosphate sharing two bonds with a single metal within the mineral surface, and the bonds are again through a mutual association of oxygen or hydroxyl. In the bottom case, we have a phosphate sharing two bonds with two metals within the mineral surface. This amounts to increasing strength of bonding as you go from monodentate to bidentate to binuclear, and that corresponds to increasing sorption hysteresis, or an increasing tendency for phosphorus to be retained against desorption, showing a level of irreversibility in sorption. I'd like to address crystallographic control of phosphorus sorption sites and use kaolinite as an example. This is a scanning electron microscope micrograph of kaolinite crystals. And here is the kaolinite edge, or the edge of the crystal, where phosphorus sorption occurs, because aluminum at the edge is undercoordinated because of broken bonds. And ligands from solution can complete the six-fold coordination for aluminum, which is its most stable coordination in association with this mineral. Energetics favor phosphate as a ligand displacing hydroxyl or water. Here I have a depiction from the side view of the kaolinite structure, and the arrow showing toward the interior of the kaolinite crystal. This is one layer of kaolinite. We have in the interior of the crystal the aluminum that is completely coordinated six-fold in the structure, and it's happy that way. But at the edge, then we have sites where sites where phosphate can bond with the aluminum and complete the six-fold coordination, where without that association, there's incomplete coordination for aluminum, and the phosphate bound there is held relatively tightly. But a good part of the surfaces of kaolinite, a good fraction of the surface area, would not be subject to phosphorus sorption because all the coordination is complete along the surface, as opposed to the broken edge itself. So what are the relations between soil components and P retention? I want to start with amorphous iron and aluminum oxides, which are very important components in Florida soils with respect to P dynamics. You're likely to find these components where you see bright colors, and you're likely not to find them where you see white or very light gray, indication of very strongly developed E horizons. Some facts about amorphous iron and aluminum oxides: they have a high specific surface area because of their amorphous nature. They don't have crystallographic constraints on undercoordinated sites for ligand exchange, as was the case for kaolinite, the example I just gave. They're responsible for the most tenacious phosphorus binding in soils, both sandy and loamy horizons of Florida. They control how much phosphorus can be added prior to a steep solution elevation, which has environmental consequences. They are extracted selectively by ammonium oxalate, and they are proportionately higher in the clay sandy horizons where they occur as binding agents for the sand grain coatings. The data below were collected for a variety of Florida sandy soil horizons from diverse locations throughout the state. These samples had some degree of sand grain coatings. The oxalate that is given on the x-axis, oxalate extractable aluminum and iron, as I mentioned before, is selective for extracting amorphous metals from metal oxides. And the relative phosphorus retention here on the y-axis is the percent of phosphorus initially in solution that is absorbed by the soil. Amorphous iron and aluminum oxides are important in retaining phosphorus up to environmentally relevant thresholds. This is a plot of water-soluble phosphorus versus the phosphorus saturation ratio, or PSR, defined as the molar ratio of extractable phosphorus to extractable amorphous aluminum and iron. Note that the PSR has a threshold above which the water-soluble phosphorus begins to increase fairly rapidly. That threshold is also known as the change point. It's possible to calculate the amount of phosphorus that can be added prior to reaching the threshold using a concept called the soil phosphorus storage capacity, or SPSC. Detailed explanation and references for the PSR and SPSC are provided in Module 4 of this series. Note that the plot represents a lot of data. These are all samples from Florida. The red symbols indicate surface horizons and the blue subsurface horizons. There are a lot more surface horizons that are elevated in PSR and water-soluble phosphorus than there are subsurface horizons, although quite a few of the subsurface horizons are also elevated, indicating that phosphorus is moving to reach those horizons. Sandy soils with coatings vary in abundance of amorphous aluminum and iron oxides. Hence, the potential of sandy soils to buffer phosphorus in solution can vary appreciably. And as I've said before, sand is not a sand, it's not a sand. Sands exhibit a fair range in their properties with respect to phosphorus retention. This is a generalized expectation of relative phosphorus sorption for samples with varying amorphous coatings. Here I have phosphorus sorbed on the y-axis and solution phosphorus concentrations on the x-axis. And we would expect the sorption to be greater where you have amorphous metal oxides in abundance, as opposed to when they're sparse. I'll move on from amorphous iron aluminum oxides to crystalline iron oxides, which, like the amorphous forms, are likely to be found in soils with color, brownish colors, in the case of sandy materials that have coatings, and also in BT horizons. but they're not going to be found in soils in Florida that are white or light gray, strongly expressed E horizons where coatings have been stripped off completely. They're less tenacious in binding phosphorus relative to amorphous iron aluminum oxides. They will absorb appreciable phosphorus at higher concentrations, though, and that means that they'll enhance P absorption max, or the S max as determined on a phosphorus absorption isotherm. These high absorption values would be at concentrations higher than what would be of relevance for soil solutions, however, and that level of absorption is not likely to be realized in real soil situations. Crystalline iron oxides don't control the phosphorus saturation ratio change point or threshold that I mentioned a few minutes ago. They are proportionately higher in BT horizons than in overlying sandy horizons. Secondary phyllosilicates such as kaolinite and hydroxylated vermiculite also impart some phosphorus retention capacity to soils. They are found in soils that have color, such as the E horizons of sandy soils that have coated sands, and particularly in BT horizons of these soils. But they're not found in the highly developed E horizons where coatings and all fine material has essentially been stripped out. They have a lower phosphorus retention capacity than amorphous metal oxides. However, they will absorb appreciable phosphorus at higher solution concentrations, which means they'll enhance the phosphorus absorption maximum, or Smax. Even though they will absorb phosphorus at higher concentrations, these concentrations are not particularly environmentally relevant, that soil solutions are not going to experience those concentrations. Therefore, the full absorption capacity of the soil at those higher concentrations are not particularly relevant for environmental considerations. They don't control, secondary phyllosilicates don't control phosphorus saturation ratio or change point. Kaolinite happens to be proportionately higher in the clay of BT horizons, whereas hydroxylated vermiculite tends to be proportionally higher in clay of sand grain coatings. My take-home points are that phosphate species tend to form strong bonds at the surface of minerals containing iron and aluminum. Phosphate tends to bond at edge sites of phyllosilicates such as kaolinite or hydroxylated vermiculite, where the aluminum exposed has incomplete coordination. Amorphous iron aluminum oxides associated with grain coatings exert strong control on phosphorus absorption in Florida sandy soils. And there is a threshold molar ratio of extractable phosphorus to extractable amorphous aluminum and iron, above which phosphorus is abruptly released more readily.